and today we are going to solve a problem about inductors.
Okay. Thank you, Bradley, for the introduction. Okay, you guys, this is from Chapter 6, problem number 7. And this took me a long time to solve, so yeah, this was a long one. So what we have, the information we have is at time 0, I of t is 40 milliamps. At positive time, we have the current is I of t is equal to A1 e to the negative 10,000 t plus A2 e to the negative 40,000 t. That's our positive time. Voltage across the inductor is negative 68 at time 0, and the inductor has inductance of 20 millihenries. So we need to find for part A the general equation for inductor current and general equation for inductor voltage. Part B, we need to find time when the inductor stores energy and time when it starts to deliver the energy. In part C, we need to show that energy stored at time 0. We need to show that energy stored in the inductor is equal to energy delivered throughout time. So energy stored is equal to energy delivered. Please be quiet, Bradley. Okay, so yeah. So the way you're going to do that in part A is we have A1 and A2, that's two unknowns, which means we need two equations. So your strategy, one strategy you can take is set I at time 0 equal to 40 milliamps. The e's will go away and you'll have one equation for A1 and A2. You'll do the same thing with voltage. You'll need to do a little bit of calculus to find the voltage because V is equal to L di dt, but that's very solvable. So you're going to solve that. Set the time to 0 when you know that it's negative 68. That will give you your second equation, and with two equations and two unknowns, you will be able to find the values for A1 and A2 and come up with general equations for current and voltage. For part B was harder because we have to take a look at what the current and the voltage is doing. We need to take note that P power is equal to voltage times current. So what you're going to do is you're going to find when the current function is 0, because before, when the current function is 0, if you actually graph, my TI-89 actually crashes when I try to graph these functions, but there are really great calculators out there. There are really great calculators, not calculators, but free internet programs like GeoGebra that you can download for free, and you can graph these. I recommend that so you can see what's happening. But the current function, if you graph that, is going to be a decreasing function. It does this kind of behavior. So, and what I did was, because my TI-89 kept crashing and I didn't really want to download the free calculator, I just found when the current function was equal to 0, took a look on took a value a little bit to that left and a little bit to the right to see whether it was a decreasing or an increasing function, and the current is doing like that, right? And then the voltage function is going to be doing like that. So wherever is 0, wherever the current is 0, to the left of that function is going to be positive, the current is positive. To the right of that, the current will be negative. And voltage to the left, where the voltage function is 0, the current is negative. And then to the right, where the function crosses 0, the voltage will be positive. So, and then you'll take a note, you're going to examine those intervals and just make a note that power is equal to voltage times current, and take a note of when power is negative. Negative power means the inductor is delivering energy to the circuit. When the power is positive, the inductor is absorbing energy or receiving a charge from the circuit. So that's how part B works, and it took a long time. That one's going to take some time. Part C, well, omega is energy is just going to be 1/2 Li squared, so you can easily find the initial energy stored by plugging in numbers for that. And energy delivered is much harder because you have to integrate power. So and power is equal to voltage times current. So you're going to integrate power, evaluate for 0 to infinity to find out how much energy is delivered to the circuit. And that is going to come out to, of course, being equal to the energy stored. It has to. You can't create energy. Energy stored is going to be what is dissipated over time. So pause the video, try all of that, and then check back and see if you did it right. Again, this problem took me a long time to do, an hour. So part A, we've got, we need to find the general equation for the equation. And so, like I said, we know that at times 0, we're at 40 milliamps, so we're going to set everything to times 0. We've got A1 e to the 0 plus A2 e to the 0. That's going to equal to 40 milliamps. But e to the 0 is just 1. So our first equation, our number 1 equation is A1 plus A2 is equal to 40 milliamps. For the voltage, we need to do a little bit of calculus, very little, but remember, voltage is equal to L di dt. L is 20 millihenries, and derivative of I is going to be negative 10,000 A1 e to the negative 10,000 t. And then the second half of that, the 20 millihenries is going to distribute through. Second half of that is going to be a 2 negative 40,000. Let's say 2 negative 40,000, not minus 40,000, but derivative of e to the negative 40,000 t is negative 40,000 e to the negative 40,000 t. Okay? When you distribute all of that through, you will get 20 millihenries, so we're going to get negative 200 A1 e to the negative 10,000 t minus 800 A2 e to the negative 40,000 t. Okay? Now we know voltage at times 0 is negative 68, so we are going to evaluate times 0. Evaluating at times 0, the e's will go to 1. This is going to give us our second equation, which is negative 200 A1 plus minus 800 A2 is equal to negative 68. Now you've got two equations and two unknowns. You can plug that into your calculator. And when you do that, you will come up with values of A1 is equal to negative 0.06 and A2 is equal to 0.1. Okay? All right, so our general equations, when you put the A1 and A2 where they belong, our general equation is I of t is equal to negative 60 e to the negative 10,000 t plus 100 e to the negative 40,000 t milliamps. And for voltage, this is going to be 12 e to the negative 10,000 t plus minus 80 e to the negative 40,000 t volts. Okay, that's part A. Part B is much harder. Part B, we need to find where I is equal to 0. We also need to find where V is equal to 0. Because I is an increasing function. Knowing where I is equal to 0 will tell us where it's negative and where it's positive. V is an increasing function, right? So knowing where V it crosses, and they don't necessarily, I made it look like an X, but actually they don't cross at X at all. They don't cross at the same place. V, where V crosses 0, right, will tell us where V is negative and where voltage is positive. Now, why do I want to know that? because P is equal to VI. I need to find the signs, because when P is negative, I am delivering a charge to the circuit. Where P is positive, I'm absorbing, the inductor is absorbing, absorbing energy from the circuit. So that's why we need to find the signs of V and I. So, and to do that, we need to do a little bit of calculus. So set I to 0, negative 60 e to the negative 10,000 t plus 100 e to the negative 40,000 t equals 0. At what time does the current equal 0? It happens at 60 e to the negative 10,000 t is equal to negative 100 e to the negative 40,000 t. We're going to divide both sides by negative 100 e to the negative 10,000 t. When I divide this side by that, by this number, I'm going to get negative 60. Well, actually, I'm going to get 60 over 100 is equal to e to the negative 30,000 t. We're going to take the natural log of both sides. Over here, taking the natural log means the t comes down, so t is going to be the natural log of 60 over 100 divided by negative 30,000. I'm assuming you have some understanding of calculus, but if not, you can watch some videos on how to do solve problems with natural log. But if you're at this level of electric circuits, you should be comfortable, and these steps, you should understand how to do that, because it's very basic calculus. If you don't and you're moving forward in engineering, I strongly suggest taking calculus because you'll need it for engineering. So that T is going to be, that T works out to be, so I is equal to 0 when T is 17.03 microseconds. Okay? That's when I is equal to 0. I'm going to erase this other information because we don't have space. So when I, over here, I crosses 0 when T is equal to 17.03 microseconds. Now we need to find where voltage crosses 0. Voltage crosses 0. So we're going to set voltage equal to 0. We've got 12 e to the negative 10,000 t minus 80 e to the negative 40,000 t. Set that to 0. We want to know the behavior of this function. So this gives me 12 e to the negative 10,000 t is equal to 80 e to the negative 40,000 t. Divide both sides by 80 e to the negative 10,000 t. On this side, this will give me 12 over 80. On this side, this will give me e to the negative 30,000 t. We're going to take the natural log of both sides. Right? Take the natural log of both sides and solve for t. This is going to give me t is equal to the natural log of 12 over 80. Divide it by negative 30,000. Okay? When you put that into your calculator, you will see that voltage is equal to 0 at time voltage is equal to 0 at time 63.24. At time 63.24 microseconds. Okay, now we're going to make a table and examine these values. Make a table. We want to know the time interval, what the current is doing, what the voltage is doing, what power is doing, and then the behavior. Okay, so So we have a couple time intervals to consider from 0 to 17.03 microseconds. From 17.03 microseconds to 63.24 microseconds. And from 63.24 microseconds to infinity time. Okay? Okay, so T current is 0 when time is 17.03. That means before current is a declining function. So before time 0, it's positive. And then after, before it crosses 0, it's positive. So and after that, it's going to be negative. Voltage is an increasing function, so before 63.02, it is positive, and then after that, it is negative, so it's positive here, negative here. Power is voltage times current, so it's positive here, positive here, right? Because the negative times the negative is positive, and the behavior is going to be when power is positive, it's delivering, and storing, and that when power is negative, and delivering. Okay, so there you go. That is the behavior. So the answer to number 2 is, it's going to be a little table that looks like this. Time 0 to 17.03 microseconds. The inductor is delivering. The circuit is delivering energy. And then from 17.03 to 63.24 microseconds, it's absorbing. And then from 63.24 microseconds to infinity, it's delivering. Okay. That is part B. Part C is to show that energy stored is equal to energy delivered. The first part is easy, the energy stored, right? Because omega is equal to 1/2 Li squared, right? And that's 1/2, 20 millihenries. And we have 40 milliamps. 40 milliamps, right? That's just a number. And that number is, and this is omega at 0. At time 0, how much energy is stored? And that number is 16 microjoules. That was the easy part. So, omega stored is equal to 16 microjoules. Now, the hard part is energy delivered, right? So here we use the definition. Omega is the energy is the integral of power. And power is of course voltage times current. So now we have to integrate that function. So that means we need to find omega, and we need to integrate from 0 to infinity to find the energy that's delivered across the circuit. So we've got, here's current, negative 60 e to the negative 10,000 t plus 100 e to the negative 40,000 t times voltage is 12 e to the negative 10,000 t minus 80 e to the negative raised to the negative 40,000 t dt. Okay, that is going to be the integral from 0 to infinity. When you FOIL that, you'll get the integral of 0 to infinity of negative 0.72. Remember that this is in milliamps, so you actually need to convert this to amps. So let's go ahead and do that conversion right here. Negative, actually, you know what? I'm not, because I can't do these things inside my head. But convert that into amps, because we need amps. We need the current, the units to be consistent. So 0.72 e to the negative 20,000 t minus, this is minus 6 e to the negative 50,000 t minus 8 e to the negative 80,000 t dt. When you integrate that, you will come up with negative 0.72 over negative 20,000 t minus 6 e to the negative 50,000 t. That's over negative 50,000 t. See, positive, negative. Okay. Sorry, this should be a positive. This should be a positive. Negative, positive, positive, negative, positive. Okay, and then this will give me negative 8 e to the negative 80,000 t over negative 80,000. Okay, we're going to integrate that from 0 to infinity. And I'm missing an e here, e to the negative 20,000. At infinity, well, this is 0. Everything is 0 at infinity, right? Because this is really big. It's in the denominator, so it's going to go to 0. So this gives me a big 0 on the infinity end of things. Minus, at 0, everything e to the 0 power, anything to the 0 power is 1. So we're going to end up with 0.72 over 20,000 minus 6 over 50,000 plus 8 over 80,000. Now, when you do that math, you're going to come up with negative 16 microjoules, which means over time, 16 microjoules worth of energy will be delivered to the circuit. So therefore, energy delivered is 16 microjoule. So energy delivered is equal to energy stored, and there's your proof. All right, Bradley, end the video.
Thank you for watching. Make sure to like, subscribe, favorite, and comment. Thank you for watching.
Thank you, Bradley.